Hello, welcome to video 6 in the A1 series. In this action-packed video today, we're going to be doing PQ 16, 17 and 18. We're going to be talking about the experiment finding the value of G by dropping a steel ball, and I'm going to be focusing on the drawing of the graph of 2s against t squared and issues with the graph. And then I'm going to introduce you, those of you that haven't done it before, to the sine and the cosine and also the tangent. We'll be spending some time on that, so those of you that this is quite unfamiliar will hopefully find that useful. And then we're going to, using sine and cosine, we're then going to introduce resolving the motion into horizontal and vertical components. Please enjoy. Welcome everybody to video 6 in the A1 series. Today we are going to start with 3 practice questions and then do some new stuff. So we're going to start today with practice question 16. A car travels in a straight line and slows down. We're told it's slowing down, and it ends up at a final speed of 12 meters per second, and it covers a distance of 25 meters. Now, first things first, the arrow of positivity. In this case, it makes sense to make the arrow in the direction in which the car is travelling. So the displacement S is plus 25 because it starts here and finishes there. U is the thing we want. V, we are told, is plus 12, and acceleration is minus 4.3. And T, we are not told, and frankly, we don't need it. So, what are we going to use? We're going to use our favourite equation number 5. V squared equals U squared plus 2AS. Let's start by making U squared the subject. So U squared equals V squared minus 2AS. V squared, V is 12, so that's easy. That's 144. Take away brackets 2 times minus 4.3 times 25. Now, notice, we know that it was slowing down, so we know that this number is going to be bigger than that number. So we need to end up making this whole thing bigger so that becomes bigger. So we need to be adding something on here, which is good, because that's negative and that's negative, so together it's going to be adding it on. And if I do it on the calculator here, 2 times 4.3 times 25 is 215. So this becomes 144 plus 215. Plus 144, 359 is U squared, square root it, 18.9. So the initial velocity was 18.9, or technically I suppose plus 18.9. Okay, so we're going to do PQ 17. This is an interesting question which is designed to make you really think about what's going on. I'll read it first. An underground train can accelerate and slow down at a constant rate of 1.3 meters per second. So I'm just going to write 1.3 there. We'll worry about the plus and the minus a bit later. And the distance between the 2 underground stations is 720, and determine the maximum speed the train can achieve between the stations. Now you're probably thinking, hang on, they've only given us 2 things. But no, we've actually got 3, because we know that the train is going to be starting at 0 and ending the journey at 0. And the way to do this is not worry about the entire journey, but to simply worry about half the journey where it's going faster. Now, if we were to draw a velocity time graph, it would accelerate to a constant speed and come back down. This would be time along the bottom. This would be velocity. And we know that the area under the graph, all of that, is 760. Because it says so. No, it's not. It's 720. I'm so sorry. 720. What we cannot do is work on the 720. Why not? Because the acceleration is not constant. There it's positive, and there it's negative. We have got to cut this journey in half. We have got to. So we're going to look, it doesn't actually matter which one we do, we're going to look at the first part of the journey, and we know that the speed at the beginning, u, is 0. And we know the distance covered is halfway to 720, which is 360. I'll make that plus 360 because I'll have positive going in the direction of the train. So we now got three things and we should be able to solve. So let's go. V squared equals u squared plus 2as. We know what u is, it's 0, so it disappears. 2 times 1.3 plus 1.3 times 360. Let's get a calculator and work that out. 2 times 1.3 times 360 is v squared, 936. 936 is v squared, square root, and we get 30.6. So we know the maximum speed is 30.6. Let's double check it. If the maximum speed is 30.6, oh, we don't know the time yet. We're going to work that out in a moment. We know the maximum speed is 30.6. How long does it take to go from 0 to 30.6 if you're accelerating every second at 1.3? Easy peasy. Divide 30.6 by 1.3 and that'll give you the time to the halfway mark. 23.54 seconds. And again, I can double check everything. If I do 23.54 times a half times 30.6, it should come back to 360 metres, and it does. So the second part of the question is the minimum time of travel between the stations. Well, we know it takes 23.54 to speed up, so it'll be 23.54 times 2. Let's call it 47 seconds. So the answer to part 2 is 47 seconds. So one more time, we can solve it using a SUVAT, like this. Put the numbers in, find v squared first, then find t, and we're there. Another way of doing it is to simply look at this speed time graph and realise that, for example, the area of that half of that triangle there, 360, which is s, is equal to ut plus half at squared, but u is 0. So that equals half at squared. So the way I would do it actually is to draw the thing, write that down and find t first. But they wanted you to find v first. It doesn't really matter. So if we try to find t from there, let's go. 360 times 2, divide by 1.3, don't worry about signs, square root the answer, 23.5 again. It all ties up. There is no one correct way of doing SUVAT questions. There are usually several ways to get to it. It is true that one particular technique will be the quickest, but for me it's not really about speed, it's about simplicity and being able to see what's going on. So for me, doing it this way and realising the area of that is 360 and writing that down makes more sense for me first. I would then work out t, and then I would just do at to work out v. But you can also do it that way. So here we have two different approaches to the same question. I hope that's all okay. PQ18, and it concerns a bicycle, and we are clearly told in the question, this is really important, it shows the displacement of a uniformly accelerated bicycle, which means acceleration is constant so we can use SUVATs. And the graph is a rubbish graph, it's much better in the book. Time goes to 4 seconds. After 4 seconds it's travelled a distance of 12 metres, and we're interested in what goes on halfway through the journey at t equals 2, which is about there. Now, what will come as a surprise is that I'm not even going to touch the graph. I'm not going to draw tangents, I'm not going to do any of that, because you don't need to, because they, rather conveniently, have chosen a halfway time. Now, let's think about this. First thing we're going to do is we're going to work out the average speed for the journey. And the average speed of the journey is obviously 12 metres over the first 4 seconds, divided by 4. I'm not reading anything else off the graph, I'm just doing that. 12 over 4 is 3. Now, if it was constantly accelerating from 0, do you not agree that it would be doing 3 in the middle of the journey. And it would be doing 6 at the end. I know it's doing 6 at the end. It's doing 3 there and it's doing 0 there. That's a big leap. Let's think about it again. We know that the average speed is 3. If I were to look at a speed time graph for that time, there's 4 seconds. And we know the average was 3. So that would be 6 there. Because the average would be 6 plus 0 divided by 2, which is 3. So the average would be 3. So the midpoint there would be 3. So the answer for how fast was it going at 2 seconds is definitely 3 meters per second. So we're left with answers B or D. It also wants to know what the acceleration was. Now we're not going to draw more graphs and tangents for that one. We know that after 2 seconds it was doing 3, and after 4 seconds it was doing 6. That means that every second it's going 1.5 meters per second faster. So the acceleration is plus 1.5 ms to the minus 2. So the answer of the question is D, 1.5 and 3. So the answer is D. I hope everybody's okay with that. Part B, sketch a velocity time graph. Well, I've already done it when I was explaining the question to you. The velocity is a straight line against time. There's 4 seconds. There's a line going straight up and it ends up at 6. There you go. That's it. Okay, so in the book, the next thing it talks about is determining a value for the acceleration due to gravity, g, using an experiment. Now, your teacher, you're going to do this experiment in the classroom. And there are many ways of doing it, but the standard way of doing it is the release of a steel ball with a machine, and your equipment will be, 95% of you will be doing this, some of you will not, but most of you will be doing this. You get a little electromagnet and a clamp, you put the steel ball on the electromagnet, it's steel so that it's held by the magnetism, so it's held in place by the electromagnet which is on, and below it you position a trigger plate, and you hook up the trigger plate and the release mechanism to a timer system. And what happens is you come along, you press a button on there, it releases the ball, starts the clock running, the ball drops, and when it gets to the bottom it hits the trigger plate and stops the clock, and you get a readout, usually in milliseconds, of how long it took the ball to drop. And what you will do is you record the time taken directly off here, and you will record the distance it fell. The distance it fell being the distance measured from the bottom of the ball to the trigger plate, because that's the distance it actually falls. So you'll collect your data and you'll make a data table. So let's say you started with the drop being about 1 meter. And if it's about 1 meter, the time taken should be about 0.45, something like that. So let's do the time in milliseconds. 450 milliseconds, and then you did another one, 460, and another one, 445. Now, your teacher might tell you that what you should do now is look at those numbers, find if there's any anomalous data, you can ignore it and work out an average and then get an average for that distance. I disagree with that approach. My approach is simple, that when it comes to doing a graph, you put all the data points on. And the whole point of doing a graph is so that you can see the anomalous data and that you will use the general average of the data and put your line through the middle of all the data. So what do? We know that the distance displacement is ut plus half at squared, but we also know that u is 0, so we can ignore it. So it's s equals half at squared, where a is the thing we want. So if we now multiply by 2, we get 2s equals at squared. This is now a graph. If we have this as our y, and this is our x, and then that m becomes the gradient of the graph. That means that you need to put t squared along the bottom of your graph, which most people do, even though we always nag you to put the independent variable along the bottom. And the independent variable is s, because that was the thing that you were changing in the experiment. But in this case, we tend to put t squared down there and 2s up there, and you plot yourself a graph. Now here's my point. If you just plot averages, you end up with a line like that, that's fine. And what you do not then do, is what so many students do, is they look at their graph and they go, oh right, I need to find the gradient. They set their ruler so that one end is at the very top right-hand cross, and the other ruler is down here at the origin, and they then draw a line and then measure the gradient. My question is, why have you gathered all this data if all you're going to do is get one end of the line on there and one end of the line on there? It also begs the question of, have you actually done an experiment where S was 0? Of course you didn't. How do you know you don't have some systematic error in your equipment? You are absolutely not entitled to use the origin as some point of truth. It's not a point of truth for your experiment. It is totally correct that it should theoretically go through there, but this is an experiment you're doing. So you are absolutely not entitled to treat that as a point of truth, like a data point that's absolutely 100%. It's not. You ignore the origin. You have what you have, and you draw and you use all the data points that you have to draw your line of best fit. Now, I would argue, your teachers will have other views on this, please have a discussion. I would argue that what you should do is you should put on there every single data point you collected, including completely rubbish ones that are clearly anomalous. And it is my argument that by putting the anomalous data on, you can see it's anomalous, you can ignore it, you get your ruler out, and you get put it right in the middle of the data, and you draw yourself a line through there, which may or may not go through the origin, doesn't matter. May or may not go through any or all of the data points, that doesn't matter. It's meant to be a line of best fit. You will then draw a huge triangle and do rise over run. And when you do that, you should end up with a value for 2s against t squared. You should end up for a value of a. And it should come out at about 9.8ish. You'd be surprised how quickly you get, or how well it gets to about 9.8 if you use decent equipment. All right, so one more time, you plot a graph of 2s against t squared, usually with t squared on the bottom. And the gradient of the graph is the acceleration due to gravity. So if you plot all this data, 2s against t squared, plot it on a graph, and then the gradient is the thing you're after. You'll be doing this for over several days at school, I imagine. My point to you is that I want you to think carefully about how you put those crosses on the graph. It is my professional opinion that you should put all your data points on the graph. Don't do any type of averaging. Put them on and then use your eye to draw the line. And most importantly of all, do not treat the origin as some sort of 100% true data point. It's not a data point because you didn't do the experiment. So why are you treating it like a data point? You can't. Okay, that was really all the key points on that. Thank you. Okay, welcome back. We're very shortly going to start on projectile motion in 2 dimensions. And one of the first things we have to do is to take a direction of motion of the ball and turn it into what we call resolve into horizontal and vertical motion. And in order to do that, we have to use trigonometric functions. Now, this course is for everyone who wants to do physics. Most of you will be perfectly happy with using sines and cosines and tangents, but some of you will be a little shaky. So I'm just going to go over the absolute basic stuff with you today, just so that that you're ready. Now, you can skip through all of this if you're absolutely fine with sines and cosines and tangents, that's just fine. But if you're one of those students who comes into my class and then starts muttering SOHCAHTOA at me, you really need to be watching this. Okay. We're going to start with the sine. Now, trigonometry, or at the level that we're doing it, is all to do with right-angled triangles. If it ain't a right-angled triangle, this isn't valid. Yes, there are cosine laws and stuff that you can use for angles that aren't right angles, but we don't do that in physics. Here is a right-angled triangle. You know that this long side, and it is always the longest side, is called the hypotenuse. Hypotenuse. Now, if we start with this angle here, and we call this theta, from this angle here, the one that is opposite is called the opposite. Whoa. And the side that is next to it is called the adjacent. Now, I want to show you something very important. If I take an equilateral triangle of sides 2, you would agree with me that all those angles are 60 degrees. If I draw a line down the middle, cut it in half, and then take, let's take this triangle and lie it on its side. So that's that triangle laid on its side. Do you agree that if that is 60 degrees, half of it will be 30? And do you agree that that still is 2, because that's that side there, so the hypotenuse is 2? And do you agree, because we cut it in half, that must be 1? Now, the sine is the relationship of the opposite compared to the hypotenuse, where it's always being divided by the hypotenuse, which means you're always going to end up with an answer which is usually less than 1, because this is always longer than that. And in this particular case, 30 degrees, you should know as a math fact that the sine of 30 degrees is a half, because that's 1 and that's 2, and 1 divided by 2 is a half. So the sine of 30 is a half. Let's just finish sine before we go on to the others. I think we'll do it that way. So let's make a little table, and we're going to have angle down here, theta, and we're going to start with 30 as our first one, and we're going to write sine up there. The sine of 30 is a half, or 0.5. That should be learnt. If the triangle, if theta was 0, it would be like two flat lines like that, and this line over here would be 0. So you need to know that the sine of 0 degrees is 0. We just need to know that. I'll put 45 in there, I'll put 60 in there, and I'll put 90 in there. And you should also know that if you were to make the angle huge, take it up towards 90, as you approach 90, these two sides get very similar. If you got to 90, which of course you can't really do, but if you did, then these two would be the same and the sine would be 1. And let's do the 60 next. Let's think about this. One way of thinking about it is to take this triangle and look at it from that point of view there. And you know that's going to be 60. So the question is, what is the sine of 60 degrees? The sine of 60 degrees in this case would be whatever that side is divided by 2. Well, let's use Pythagoras to work it out. This is the hypotenuse. So 2 squared is 4. 1 squared is 1. 4 squared take away 1 squared is 3. So that is the square root of 3. If that side was 2, that would be the square root of 3 from there to there. So what would the sine be? The sine of 60 would be that divided by 2, square root of 3 over 2. And if you get your calculator and you type in sine 60 equals, you get square root of 3 over 2, which if you press your SD button, it's amazing how many students come into my class and they don't even know how to get their surd on there into a number. On your calculator, if you're using a proper Casio, not this Mickey Mouse Texas stuff that you use for your IB, but if you've got an old-fashioned Casio, there's an SD button which stands for surd decimal toggle. If you press it, 0.866. 0.866 is the sine of 60 degrees, also known as root 3 over 2. And the last one is 45 degrees. Well, that's easy. If I make a box, 1 by 1 by 1 by 1, and draw a diagonal, that's 45 degrees. And 1 squared plus 1 squared is 2, so we know that that is the square root of 2, which means that the sine of 45 degrees is 1 divided by the square root of 2. Now, little maths facts for you. Mathematicians don't like you putting roots on the bottom. They just don't like it. And so what they make you do is they make you multiply by root 2 above and below. So multiply by root 2 over root 2, and you get root 2 over 2. And so again, if I type in sine 45, I'm going to get root 2 over 2, which is 0.707. And there's a general rule which you should always know. 1 over the square root of any number is the same as the square root of that number over the number. You should learn that. 1 over root n is equal to root n over n. And that's the form teachers like to see it in, because that's forbidden in maths. Okay, so that's the sine. And so what we're going to do is we're now going to quickly use the sine function to work out some questions. Now, the way it works generally in physics, they will usually give you the long hypotenuse and you'll be asked to work out the opposite. So let's do a couple of questions doing that. So let's do, this is 23 units long and that is 17 degrees. What is that? Rule. Let me just do it bigger. Here's the rule for you. If you know what the long side is and you want to work out that, and this is your theta, to go that way, you're always trying to make it smaller, so you multiply by sine. So if you're told the long side and you want the smaller opposite side, you'll multiply by sine of theta. And if you're told the smaller side and you want to work out the longer side, you'll divide by sine theta. So here we're told 23. We want to make the number smaller by multiplying it by a number less than 1, which is the sine. So 23 times sine 17, 6.72. Everybody okay with that bit? We'll do one going the other way now, and then we'll have a look at cosine. So if I give you a triangle that looks like that, and it's a right angle triangle, and I tell you that that is 19 units, and I tell you that that is 78 degrees, I ask you what that is. This is longer, so you're going to be dividing this number by the sine of that number. 19 divided by the sine of 78, 19.42. Hopefully everyone's okay with using sines. Cosine is a very similar pattern. Here's a triangle, here's theta, here's the hypotenuse, here's the opposite, here's the adjacent. With the cosine, it's not this divided by that, it's the adjacent divided by the hypotenuse. I like to think of cosine starts with a C, right? What else starts with a C? A crocodile. So you can think of, I think of cosine as the crocodile function. So you've got like crocodile jaws. So it's the relationship between these two. One of the laws that you're supposed to know by now is that the sine of an angle is equal to, is the same as the cosine of 90 minus theta. What does that mean? So sine of 30 degrees is a half, because that's the sine of 30 degrees. 90 minus 30 is 60, so the cosine of 60 is also a half. Because if you look at this triangle down here, that's 30 degrees, that's 60 degrees. The cosine here would be 1 divided by 2, which is a half. 1 divided by 2. So I don't have to do any more work. All I have to do now to fill in this table for cosine is to simply use that image and do some sort of mirror image swapping. Let me show you. I know that the cosine of 0 is the same as the sine for 90, which is 1. I know the cosine of 60 is the sine of 30, which is a half. And therefore, the cosine of 30 will be the sine of 60, so that goes in there. These two are the same. And the cosine of 90 degrees is 0. It's like a mirror image, like a reflection through there. That's what it sort of is. We're going to do a few little questions, and then we're going to quickly look at tangents, and then we're going to move on for the moment. We are going to come back to trig when we start looking at, for example, later on with motion in a circle, because you need to understand the actual sine wave function and the cosine function. I'm going to put up, we're using sines and cosines here, okay? I'm going to give you 6 questions. You can pause the video, work them all out. Let's do them. Each time I'm drawing you a right angle triangle. I'll have theta down on the left hand side because it's easier. I'll tell you what theta is. 23 degrees. That is 11 units. What is that? That's question 1. Go, you can pause. Question 1. Here's the angle. This is the opposite. I want to know this one. This is a sine relationship. We're going to make it bigger. By making it bigger, we need to be dividing by sine 23. Let's go. 11 divided by sine 23, 28.2. Done. Second one. This time we want to go from there to the opposite. So we want to be multiplying by the sine. 28 times sine 55, 22.9. On this question, actually it's the same, isn't it? Oh, no, I want to go down here. This is a cosine relationship. I know that that's bigger, that's smaller, so it's going to be multiplied by cos 62 to go down there. 29 times cos 62 equals 13.6. This time it's also a cosine relationship, but I'm getting bigger, so it's going to be 23 divided by cos 48, 34.4. On this one we're going to use both. That's a sine relationship. It's getting smaller. 21 times sine 38 equals 12.93. 12.9. This one is a cosine relationship. 21 times cos 16.5. Now, if that was new to you, then you need to go back and practice these. All right, I'm assuming it's not new for you, most of you, you've done it all before. In physics, we are going to be doing an awful lot of working that out and that out by taking the number we're given, which is usually, if you like, a hypotenuse, and then working out what that and that is. That's what we're going to be doing over the next few lessons. There is a third trigonomic function called the tangent. The tangent is not often used. I'll stop now, I'll start in a moment. Okay, so the last one is the tangent, and the tangent is the only one that does not involve the hypotenuse. It's basically the relationship between the opposite and the adjacent, and many students forget which way round it is. The easiest way to think about it is that the one that's on the top is the opposite, and as this gets bigger, the tangent gets bigger, because you're going to divide the opposite by the adjacent. And the way to do this, you divide the opposite by the adjacent, that gives you the tangent of the number. So if I tell you that that is 17 and this is 42 degrees, how do you work out this? Well, I don't use maths, I just sort of like think about it. Basically, if you're going that way, that's multiplied by tangent. If you're going up to the wall from the bottom, you're multiplying by the tangent. And if you're going that way, down to the ground from the wall, if you like, you divide by the tangent. That's how I remember it. Going up, multiply by tangent. Going down, because you want the one at the bottom, divide by tangent. So if I want this down here, now, first rule, you should all know that the tangent of 45 degrees is exactly 1, because these two are the same length. 1 divided by 1. Which means that if the angle is less than 42 degrees, you would agree with me that that side will be longer than that side. If I'm telling you that that is 17, the answer to the length of that, because that's 42 degrees, is going to be slightly more than 17 degrees. So 17 divide by tan 42 is 18.9. Well, it works. 18.9. And if you go the other way, you would multiply by tangent. So we're going back to our table here. We're just going to fill in the tangent numbers for 6 values. The first thing you need to know is that the tangent of 45 degrees is 1. You should all know that. Tangent of 45 is 1. Tangents of angles greater than 45 degrees are bigger than 1, and tangents for angles less than 45 degrees are smaller than 1. When that angle is 0, then if you like, that wall there is 0, and this becomes 0. Now, interestingly, when you go to the extreme, and you set it up like that, at the extreme 90, it is true that these two are basically the same length. What's happened to that? It's gone to 0. And you are now dividing by 0, so you should know the tangent of 90 is NA. It's not available. doesn't exist. It's not infinity, it's not zero, it just doesn't exist. It's not a number, it's not a value. What about the 2 in the middle? What about the tangent of 30? Again, in maths, hopefully you have been told that a way of working out a tangent is simply to divide the sine by the cosine, because, let me just go back, let me rub this off for a second, this is quite important stuff. You know when we talked about sines and cosines, if I make on a triangle the hypotenuse 1 unit long, the sine of that angle will be that. That length will be the sine, if that's 1. That'll be the sine, and that'll be the cosine of the angle. So the relationship of this side to this side, which is the tangent, is simply sine theta divided by cos theta. So whatever sine theta is divided by the cosine of theta will give you the tangent of theta. You should know that from maths. Okay, so if we look at tan 30, one way to work out tan 30 is simply divide a half divided by that, which is the same as multiplying by the reciprocal. So if I multiply that across, I get 2 over 2 root 3. 2's cancel. 1 over root 3. And I told you earlier that 1 over root n is the same as root n over n. So 1 over root 3 is the same as root 3 divided by 3. And that, if you get your calculator out and you go tan 30, root 3 over 3. Root 3 over 3, which is about 0.577, is the tangent of 30 degrees. And the tangent of 45, oh, very messy, sorry, apologies. So tangent of 0, 0. Tangent of 30, root 3 over 3, about 0.577. Tangent of 45, we all know, is 1. Tangent of 60 would be root 3 over 2, which is the sine, divided by the cosine, which is the same as multiplying by 2. 2's cancel, root 3. Don't believe me? Get your calculator out. Tangent 60, root 3. And the square root of 3 is about 1.732. You should not have to learn any of these weird values, but you should be able to go back and, well, because you've got your calculator, but you should have a rough idea, and you should certainly know the tangent of 45 is 1, you should know that the sine and cosine of 45 is root 2 over 2, you should certainly know 30 and 60, and you have to know 0 and 90. That's basically it for very basic trigonometry. I hope that's helped a little bit. Okay, so how are we going to use our knowledge of trigonometry to help us with projectile motions in 2 dimensions? You will typically be given a question where an object is thrown. Now, first rule of projectiles, when an object is thrown, the only force acting on it during the time it is up there is weight pulling it back down. It has no other forces acting on it in physics land. In reality, there's air resistance. So let's say somebody throws an object, a ball, a football, whatever, very fast, 40 meters per second in this direction, 38 degrees to the horizontal. This 40 meters per second at 38 degrees is of very little value to us because in order for our equations to work, we've got to have constant acceleration. Constant acceleration means that you're accelerating with a constant value in a constant direction all the time. And that isn't really happening for this because it's not only going, in fact this is going to be doing a parabola and going to do that. The way to think about this is to what I call resolve into horizontal and vertical motions. And so the very first thing we are going to do is we're going to say, well, that's okay, it's doing that. What is its vertical component? And the vertical component, look at this right angle triangle, vertical component is sine 38 times 40 equals whatever that is. So at this moment, sine 38 times 40, 24. Now when I'm going to be working, I'm going to keep my calculations to 2 decimal places, 24.63. I'm going to use that number in my calculations. So I know that my vertical component is 24.63 and my horizontal component, is cos 38 times 40. Now, here's the way it works. If this angle is less than 45 degrees, then you know that this is the longer side than that. That's longer than that. So the horizontal number, when I do this, it better be a number bigger than 24 or I'm wrong. So cos 38 times 40, 31.52. Conventions. I'm probably just going to get lazy and draw an up vertical arrow to show that that's the vertical component, and draw a horizontal arrow to show that's the horizontal component. Sometimes I use V with an arrow. Once we split it into a vertical component and a horizontal component, things become very easy. In physics land, there is no air resistance. So this value, 31.52 sideways, is constant until it hits something like a wall or the floor or drops into the sea. So rule number 1 of projectile motion, everybody, horizontal motion or horizontal component of motion, horizontal component of motion is unchanging for the entire journey. If it starts off going sideways at 31.52, just before it hits wherever it's going, it'll be doing 31.52. It will not be speeding up, it will not be slowing down. Why would it? It's going sideways. Gravity acts downwards. It's not going to affect your horizontal speed. Okay, so that's rule 1. Rule 2 is that that's your vertical component. And what we basically do when we solve projectile questions, although in reality it's going like that, we just think of it as going up and down. And we sort of work it out. We work out what's happening to the vertical as though it's actually only just going up and down. And that tells us where it is at certain times. And from that, we can work out how far sideways it's gone. Okay, so rule 1, horizontal component of motion is unchanging for the entire trip. Once you've worked it out by going usually cos the angle times the number you've been given, that stays the same all the journey. This thing is going to be changing. Just to remind you, how long is it going to take before it gets to the top? Easy peasy. 2463 divided by 10. 2.46 seconds. However, from last time, I've done some research and DP students are going to be using, in my case, minus 9.8 ms to the minus 2 for the acceleration due to gravity from now on. And I am going to use that number or that value from now on in all my projectile calculations. So the question is, how long will it take this object to get to the top of its flight? Answer, its vertical component divided by g. 24.63 divided by 9.8. It will take 2.51 seconds to get to the top. 2.51 seconds. And if it's a level ground question, it will take 2.51 seconds to come back down again. That's very important. Okay, what we're going to do is going to wrap that up now, and then in the next video, we're going to start doing some proper two-dimensional projectile questions. Thank you and goodbye.